All right, welcome back. Let's get to monitoring earthquakes. This is going to be short and sweet because there's really not all that much pertinent information for your quizzes or post-tests in here. All right, so how we monitor earthquakes is through a lot of things like seismographs, tilt meters, creep meters. Um, so we'll get into seismographs. We talked about it in the previous video. How this is how like we measure the Richter scale is on seismographs. So essentially we've got this little thing here. It's got a spring coming down. It's attached to a weight and then a pen. And that pen is going to be touching this rotating drum of paper that's just continuously spinning. And any sort of motion from the earth, like from an earthquake, any sort of energy is going to make this pen move from side to side. And so what we get here is, hopefully I can go down far enough so you can see, what we get here is this little P wave here. That's that first wave, the primary wave. So with this straight line, that means that there's no seismic activity at all. That pen is just going straight. It hasn't been hit by any energy. And then we get a P wave. That's the primary wave, the first wave, the fastest wave. And you get this little bump. They're not super destructive, so there's not a lot of energy in that P wave. And then it'll go on, and you'll get this first S wave, and you can see this larger bump. Remember, from this P wave to this S wave is how they measure that distance so that they can triangulate. So remember, triangulation is just like those three circles, and wherever they all intersect is where that epicenter of the earthquake is. So this is how they do it. And then you see right here, surface waves. They're the most destructive waves. That's all that is energy that it's indicating here. So the surface waves have a lot of energy, and then it just stops. And then you'll get that line again. You might have like a couple aftershocks as well, but normally those aren't like too huge or serious. Okay, so we also measure faults. So to measure these faults, we use GPS satellites. So we just get that like bird's eye view of the fault, see if it's growing anymore, see how deep it is, that type of thing. And then we can monitor the vertical movement of a fault, and we use a tilt meter. So here's a tilt meter. They've got it set up on this section of land that they know a fault is on. And so you can see how it's like tilted a little bit that way. So that means that one side of the rock is kind of going like this. So we're getting that hanging wall and footwall are moving away. So if it's a normal fault, that hanging wall is falling down, and it's a divergent boundary. Or if it's a reverse fault, you're going to get a convergent boundary, and that hanging wall is going to go over the footwall. So right here, it looks like we've got a divergent boundary, and the hanging wall is moving down. Then we measure horizontal movement. So we can measure that through the use of a creep meter or laser ranging devices. And laser ranging devices are just, you can get a really good, like if you use a laser, you can get a really good idea of how far that fault has moved. And you can quantify that pretty accurately. And here's a creep meter. So they anchor it on one side of a fault, usually a strike-slip fault. You can use it on a divergent boundary as well. You anchor it, then you've got a wire going across the fault line attached to a weight, and that's going to measure how far, due to the tension of this wire, that fault has moved since you planted the anchor post. And so to try and predict earthquakes, it's pretty impossible. We can't really do it. We know where earthquakes are going to happen. We know what types of boundaries there are. We know what types of stress is enacted on those boundaries so that we know what type of earthquake is going to happen, whether it's a strike slip, a convergent or a divergent boundary, what kind of faults we're going to get. But other than that, we cannot really predict with very much accuracy when an earthquake is going to hit. So we map faults so that we can see the reflection of the wave, the energy that's being produced from that fault, from the focus to the epicenter to the fault. So we can kind of get an idea of like how much energy is produced from one of those earthquakes that we've already seen, and where the waves are going to radiate to. So we can map faults to kind of get a little bit of an idea of what to expect, but it's not going to tell us when the next earthquake is going to happen. And so then we monitor change along faults, like with those tilt meters and creep meters, to monitor the friction between two boundaries. So friction, we're just going to call that's potential energy. So with those strike slip faults, you know how I said before, they're kind of like moving together like this, and then they have all this friction built up, and at a certain point there's going to be a release of energy, and they're going to move this way, opposite of each other. And that release of energy is going to expand all across in all different directions, and those are seismic waves. So we can monitor the change along faults to kind of get an idea of when to expect a fault, but it's not very absolute data. You can't quantify it all that well. But if you know that there's like a pretty good change along two fault lines, then you know that there's a good amount of potential energy in that system. So you could be looking at a significant earthquake in the near future. So the takeaway here is that we cannot accurately predict when an earthquake is going to happen, but we can accurately predict where it's going to happen or how much energy will be released. It's not super accurate, but that's just because these things happen pretty instantaneously. The Earth's plate tectonics are so enormous that when any small movement happens, it's a release of a lot of energy. And so here's just a little graphic of just faults. So we've got this Cucamonga fault zone, and all around here we have all these strike slip faults. So we know around here that there's going to be a lot of friction. So if we can put a creep meter here across to here, and we notice that this area is moving a lot, then we know that there's probably going to be a quick release of energy in the near future. So we're going to see probably an earthquake happening in this area relatively soon. So you need to prepare for it, but we can't tell you if it's going to be tomorrow or if it's going to be in 10 years. So that's the only problem with that. So that's all you're going to need to know with the prediction and the forecasting of earthquakes and how we measure them. So if you have any questions, comments, concerns, go ahead, let me know. And other than that, good luck on your quiz and test, and have a wonderful week.